Good morning. John Gilkison, AeroStealth here. And it is Monday, July 29th, 2024. And I wanted to do a video today on the power of aerodynamics. Now recently, a good friend of mine, Phil Knox, who I collaborate with on aerodynamics, he provides data and information for my presentations. He did a whole expose on the Ioniq 5, which we own. And here's a road load graph right over here for the Ioniq 5, which I like to make them glove box size, laminate them, and put some data tables on the back. They're really cute, and not only that, they make great Christmas tree ornaments. You punch a little hole in the top and you can hang it from your tree. It's colorful. So, but the whole point of his exercise was to go through not only the Ioniq 5, but he also did a road load graph, or not a graph, but tables on the Ioniq 6. As you can see here, there's his tables for doing a graph, but he didn't do the graph for it. And then he went ahead and fleshed this out further, because the Ioniq 6 has a drag coefficient of 0.219. Just call it 0.22. There was a car GM made in 2002. It's called the GM Aero Body. There's a silhouette of it. You can see right at the rear, this is the amount of taper that would be, residual taper, that would be necessary to bring the air back together. You can see on the Ioniq 6, it's substantially larger. It means the wake area of the car is larger. And the Ioniq 5 has an even larger wake area and would require quite a substantial boat tail to bring the air back together. So he went ahead and did the GM Aero Body, which I'm not a big fan of, but it's really good for comparison purposes. And not only that, one of the features of the car, which I like to point out, this is back in the air in the time period when internal combustion engines ruled. But you can see there's quite a bit of forebody. This is the area, typically a hood, it's where you'd have a gasoline engine. And consequently, and then the windshield's back up here. And what you end up with is wasted space forward. So the vehicle has to be longer to get this taper. If you get rid of that, and you go to what's labeled as a CUEV shape, which stands for Cambridge University this will be an ideal shape, and what you have here is a cab forward, so you get rid of the hood and stuff, because with electric drive you don't need to necessarily have a motor. The motor can be where the wheels are, and the components can be anywhere, you know, the inverters and coolant loops, all that. You need some coolant loops up front, obviously, where the air intake is, you know, for radiators and such. But this shape here has a drag coefficient of 0.12, while this shape here has a drag coefficient of 0.15, and the Ioniq 6 is 0.219, as I pointed out, and the Ioniq 5, which we own, I have the taken some of the paper out of this. It has a drag coefficient of 0.288. So, what's the consequences of lowering the drag like this? All of these shapes that he's graphed out are based on the idea or the premise that you would still have the Ioniq 5's battery pack and powertrain, and all that would be the same, and the mass would be the same, more or less, and the rolling resistance would be equivalent. So how would the improvements in aerodynamics, the reduction in aerodynamic drag, improve the range of these vehicles? And that's why I've given this video a title of The Power of Aerodynamics. It's because as you keep lowering the coefficient of drag of a vehicle, the road load, the amount of horsepower or kilowatts it takes to propel a car drops at any given speed. And this has consequences. In this instance, it can double the range, and the battery's no larger. And so I wanted to go through that. I think this is important, and it's something that's still missing on a lot of the discourse that you see nowadays. Now this is my graph right here of the Ioniq 5. As you see, it's quite tall. The blue is the rolling resistance right here. Now, you may notice this over here. The blue over here in this graph, which is a graph of a body shape that's 0.10. This is the only one I could find that I had on hand, so I wanted to use it. It's not exact for the CUEV shape, but one of the points I would like to make here is that the rolling resistance looks quite large. It's really not. It's just large in comparison to the amount of load that aerodynamics plays. In other words, at higher speeds, the aerodynamic loading is much greater on a higher coefficient of drag shape than it is on a lower one. And so it proportionally, the rolling resistance proportionally keeps appearing larger. And also these graphs have to change scale, as you can see. How many boxes I have on this one compared to this one here. So, and just for example here, we have, this is 0.13. Coefficient of drag, which is close to the 0.12 that we're talking about, the CUV shape. So I'm going to leave this one out for now, just so you can see what I mean. So this would be the two together, like so. Okay? So, and one of the things that happens is you have to view these as if, let me show you this first. This is the data table for the graph. And he has on here aerodynamic horsepower, rolling resistance horsepower, and then the total, the road horsepower, and then the brake horsepower, which is the final figure at the rear wheels. And then he expands it out into watt hours on any given speed for the range. And by range, we mean the total range of the battery. And he used 77.4 kilowatt hours, which is the battery size in the Ioniq 5. However, I informed him that the usable battery was 74 kilowatt hours. And so he goes ahead and produces tables of watt hours per mile, miles per kilowatt hour, and then the range. So, for example, at 75 miles per hour, which he has highlighted in yellows here, which is a good interstate speed, the vehicle would have 262 miles of range. And it would essentially it would make about 3.4 kilowatt hours, miles per kilowatt hour. So now I took issue with some of this. Number one, because of the usable battery only being 74, so that changed the range figure. And so I went ahead and I produced a table of my own. I didn't alter anything but the range numbers here. So as you can see, but I added, because no one drives a car from 100% state of charge down to 0, unless you're some of these idiots on YouTube who are trying to brick a car and show just the absolute maximum distance it can go, which is anecdotal because it's on any given day with any given set of conditions and so forth. And I think it's a ridiculous experiment to pull. They get to DC fast charger and they still got range left, and they're driving around the block for 10-20 minutes to burn up the rest of the battery, and I just think the whole exercise is absurd. It's my opinion. However, what we do is if you charge to 100% and you go off on a trip, you might set 10% as your acceptable range to be at when you get to a DC fast charger. And that gives you a margin of error so that you don't end up running out of juice before you get to the charger. So that would be 90% of the battery. And then once you're on the road, you charge to 80% normally, and you drive to 10%. Well, that's only 70% of the battery. So what I did was I went ahead and I kept the total range, but I produced this range figure right here using the 74 kilowatt hour battery pack, not the 77.4. And then I went ahead and produced 90%, 70% figures, which I think is more realistic. And so that's what ended up on the back of my little tote around road load graph. Now, even that's not fully accurate because it doesn't include ancillaries. If you're going to run the air conditioner or the heat, it's, by definition, you can't include these things anyway because they're variables. In the shoulder seasons, you might not use anything but cabin ventilation. You're just running a fan. You can have headwinds, you can have tailwinds, you can have crosswinds. You can be at 8,000 feet driving. You can be at sea level driving. The temperature can be 110. The temperature can be 10 degrees. There's just every kind of factor that's possible, and you cannot produce tables or write graphs for all of it. You could produce tables for all of these, but it would be quite an extensive piece of work. You can't incorporate it all into one graph normally. So this is the way to go. You produce your road load graph based on mathematics, on the forces, the counter forces of aerodynamics and rolling resistance. And that's it. You don't include ancillaries or anything else. So I went ahead, and I still didn't include ancillaries, but I went ahead and produced a table on the back and only for 90 to 25 miles an hour. I just needed to fill up the space. And I did 90% of the range and 70% of the range, which I think is useful information for a person operating a vehicle. It's helpful. So let's get into a few of these numbers. I got, so with the Ioniq 5, just as it is, as I told you, it's at 75 miles an hour, 90% battery, and I'm going to give you 90% battery and 70% battery. I'm not going to talk about the range and 100%. At 75 miles an hour, it would have 225 miles of range and 175 miles of range at 70% battery. And this is very usable. I mean, chargers are usually closer together than that. You have to be in a real charging desert to run across chargers more than 175 miles apart. So, but if you just slow down to 65 miles an hour, you have 283 miles of range and 220. So there's your answer. If you have a headwind, let's say you're out there driving and you have a headwind of 10 miles an hour. The answer to that is to slow down 10 miles an hour, if you know that. If you have a tailwind, you can literally go a little bit faster, and it's the equivalent. If you're doing 60 miles an hour and you got a 10 mile an hour tailwind, it's the equivalent of doing 50 miles an hour. So you could do 70 and you still have the equivalent of 60. So we give it down to 55. At 55 miles an hour, we have 360 miles of range and 281. So you see, we're in that sweet spot. We're in the high 100s at 80% charge, down to 10%. And we're up to as much as 360 miles of range if you slow down to 55 miles an hour, which you're probably normally not going to want to do unless you're on roads that are posted to do that. So there's a big difference. If you merely switch to an Ioniq 6, which we test drove, I didn't buy it. I was intrigued by the aerodynamics, but I didn't buy the car because I didn't like the way it was laid out. It was personal. I just like the ergonomics of the Ioniq 6 better. I didn't like this bridge in the front that takes away your space in between the passenger and driver's seat. So, but the Ioniq 6 is 75 miles an hour. Here's the Ioniq 6. Okay. And you can see that perfect shape behind it. 75 miles an hour, 280 miles of range, 218. So already, just by driving a vehicle that has the same frontal area, but it has a coefficient of drag that's 0.2, forget exactly what it was, 0.219, that's it, versus 0.288. It's bumped your range up from 280, I think, miles up to 311. So you've gained 30 plus miles of range simply by having a lower drag coefficient. This is at 75 miles an hour. At 65, you're at 346 miles of range and 269 at 70% battery. And at 55, you're already up to 433 and 337. So at 55 miles an hour, you're literally getting into trips where you don't even have to charge. But most of us don't want to drive 55 miles an hour. I don't. So let's move on to the GM shape, which lowers the drag coefficient down to 0.15. Here it is. 75 miles an hour, 90% battery, 270 miles of range, 280. 65 miles an hour, 446 miles of range, 347. 55 miles an hour, 542 and 422. Same battery, same powertrain, same car body size, same frontal area, just a lower drag coefficient. Okay? Now my favorite is this last body, the CUEV shape. The reason is I think it just gets into magical territory. This is a 0.12 drag coefficient shape. And this is probably what's practical. You'd get rid of the mirrors, you'd even get a little bit more if the government would let us do it, but they won't so far in the United States. Here's the body shape, just to remind you. 75 miles an hour, 90% battery, 426 miles of range. You might remember the Ioniq 5, the original one. $225 miles of range at 90% battery for the Ioniq 5. 426, 75 miles an hour. That's the power of aerodynamics right there. Quite simply, this is a car you could charge to 100%, get on the road, drive it down to 10%, drive over 400 miles. Be at your destination. Do destination charging overnight. There you are. The Holy Grail. I just don't know how much simpler that could be. And I don't know why it's not understood. Now, there would be some objections to this car because of this long tail. However, what you need to understand about that long tail is that could be detachable. In other words, you could take it off from here back for local driving. There's no need to have a tail like that unless you're on the highway. If you're traveling somewhere, it's not an issue. Once you get to your destination, now it could be foldable or whatever. You might have it pneumatic. It could be inflatable, which I don't care much for because that's fraught with difficulties about leaks. But if it was foldable, it could tuck away. Mercedes-Benz done some work in that area. Or it could be foldable and detachable, and you could put it in the trunk of the car when you're traveling. When you're around town, you just don't need that long shape. It is a problem in city traffic and so forth. Someone might run into you just because they're not aware of what the hell that thing is. So, however, on the highway, this is really something. Now, if we had I don't have this up here. I only went up to 90. But if we had highways where you could do 90, like a lot of people already do, 90% battery, 334 miles of range. That's greater than my car has now at 75. And the aerodynamic drag really goes up tremendously at those speeds. I mean, you can see it on the graph. If I just knew what I did with the graph. Here it is. Let's stick this on here. Here it is right here. 100 miles an hour. 45 kilowatts. You have to multiply 45 times 1.34 to convert that into horsepower. 90. We're at about 35 kilowatts. That's with my car as it is currently. Now understand this. Even a gas car requires the same horsepower. It doesn't matter what the power source is. This is your aerodynamic loading. This is your rolling resistance. Just think of it as, forget all about the power source. Think of it as a magic rope, an invisible rope hooked up to the front of your vehicle and it's towing it down the road. You cannot see it. It's got a Klingon cloaking device on it. And, you know, the god of aerodynamics is towing you down the road. That's it. That's your road load. That's your rolling resistance. And you turn on ancillaries, those are a load. Depends on what you turn on, what the ambient conditions are. Other factors, as I pointed out, elevation, wind direction, temperature, so forth. These are all going to add up, and you just can't graph and chart them all. So there you have it. That's the power of aerodynamics. We could literally double the range of electric vehicles by going to low coefficients of drag. And by low coefficients of drag, I mean lower, again, by a full point over what Tesla's doing. Tesla hasn't pulled out the stops. They haven't cornered the market on this. And I know Aptera is out there trying to do something like this, but I'm not a big fan of the Aptera because of, I think, its crash worthiness. So I'll let you go. I got a phone call coming in. So bye.